Let's look at molecular strength of acids. So we're going to start with two factors that influence ionization of a binary acid: the strength of the HX bond and the polarity of the HX bond. So if the HX bond is a strong bond, it does not want to break. That makes it a weak acid. So if you think of an acid as able to give off H+, this acid is not wanting to give off H+ if it's a strong bond, which is why it would then be a weak acid. This explains why hydrofluoric acid is classified as a weak acid. It has a bond strength greater than the other halogen acids. The other factor is, staying on this factor, if you compare that HF is 569, whereas HBr is 368 kilojoules per mole, that should be over here. That is a huge difference. So if this is a weak bond between the hydrogen and the X, then H+ will come off because the bond will break easily. So weak bond, strong acid. So again, we're trying to explain why hydrofluoric acid is weak. It's because it has a strong bond and the H+ is not going to come off as much. So strong bond, weak acid. Whereas the rest of the halogens have a relatively weak bond, which makes them a strong acid. So that would be the HCl, HBr, HI. They would all be strong acids because their bonds are relatively weak. The other factor that influences ionization of a binary acid is the polarity of that HX bond. The more polar the bond, the stronger the acid. So think of it this way. When this is an acid, we want the H+ to come off, and if you're already pulling on the electron of the H, then it makes it easier for the H+ to come off. So let's look, for example, at a hydrogen that's attached to a carbon. That is a relatively nonpolar bond, and the hydrogen on the carbon is not acidic. This is the electronegativity value of hydrogen, 2.1, and carbon is 2.5. Whereas if you look at this hydrogen that's attached to an oxygen, the hydrogen-oxygen bond is polar, and this hydrogen attached to the oxygen is acidic. The electronegativity value of hydrogen is 2.1, and oxygen is 3.5. Okay, let's look at another situation. So if you're looking at acidic hydrogens, so for example, we just said that a hydrogen attached to an oxygen is acidic, but the oxygen in turn can be attached to another atom. We're calling that the atom Z. As the electronegativity of Z increases, the OH bond becomes more polar and therefore a stronger acid. So what we're saying is that the atom attached to the oxygen, which in turn is attached to a hydrogen, can affect the acidity of the acid. So let's look at a question. The question is asking us to put these acids in order of increasing acid strength. So that means that we want to have the weakest first and then the strongest. So let's look at the acidic hydrogen. So this would be an acidic hydrogen here. And then this is our acidic hydrogen here. And then we'll just pick one of these. So this hydrogen is attached to an oxygen, as well as this hydrogen attached to an oxygen, and this hydrogen attached to an oxygen. We just said that you can look at the atom that the oxygen is attached to. So in this case, for carbonic acid, the oxygen is attached to carbon. For nitric acid, the oxygen is attached to nitrogen. And for boric acid, the oxygen is attached to boron. So these all have a hydrogen-oxygen bond, but we have to look at what atom the oxygen itself is attached to. We are calling that atom Z. That atom is pulling electron density away from the hydrogen. It's splitting off the H+, the acidic hydrogen. Whichever Z atom is the most electronegative, that is the strongest acid. This idea of pulling electron density through sigma bonds is called an inductive effect. So that means that we need to know the electronegativity values, or you could really use the trends in the periodic table because these atoms are all in the same period. So if you look at where they are in the same period, you would find that nitrogen is farther to the right of carbon, carbon is to the right of boron, and so nitrogen is more electronegative than carbon, carbon is more electronegative than boron, and so if we're putting the weakest first, that would be the boric acid. So without even values and using the trends in the periodic table, you would say the boric acid is weaker than carbonic acid, is weaker than nitrous acid. So let's see what the situation would be if you had the same central atom, but you had different number of oxygens. So in that case, we would look at the acidic hydrogen. Let's find it. So let's choose this one as the acidic hydrogen. And this one is the acidic hydrogen. And then we notice we have 1, 2, 3, 4 oxygens here. 1, 2, 3 oxygens here. So our central atom is this one, the sulfur. And again, the sulfur. So when we have the same central atom, but different number of oxygens, the greater the number of oxygens, the stronger the acid. Because the oxygen is electronegative, it's pulling the electron away from the hydrogen. But what we're saying is this oxygen has the help of 3 other oxygens, whereas this oxygen only has the help from 2 other oxygens. Okay, we'll do acid-base properties of salts next.